Sorry, can I ask the last question if you don't mind?
We'll both be together for at the end part.
Will you change the slides or, oh, okay, great. So I will focus my part of the talk primarily towards federated learning with multiple institutions. But before I jump into that, I want to mention that we did do another layer of study for COMAP. The validation, actually, we did COMAP validation at also at MGH, MGB and the VA using chart review results, as well as at Boston Children's. They all did reasonably well, particularly compared to fee code. But this is another validation that we did. We actually ran a FIWAS using the statin variant. As we all know, the statin targets that particular gene, and the mechanism is lower LDL. But as a result, statin has a protective effect against multiple phenotypes, including, for example, cardiovascular disease. Here, we are just trying to show what benefit do we get if we run a FIWAS using statin variant for a minority population. Here, we're just looking at a smaller subset of patients who are of African descent, using the biobank data from Mass General. So you can see on the left-hand side is the FIWAS result using the fee code alone for all the phenotypes, basically about 1,600 phenotypes. On the right-hand side is basically using COMAP. You can see that in terms of the significant signal. So there's a substantial difference between the accuracy of the phenotype. But I want to focus my presentation primarily towards federated learning. So one thing I'm sure most people here are experts in, like EHR data, and even though we use I2B2, there's still a huge amount of human effort needed to harmonize data. For example, we mentioned A1C. Actually, the most interesting exercise I did was actually ESR and CRP. I did a project with Ken Mendel trying to build a knowledge graph for pediatric population, and my goal is to show what are the differences between the adult population and pediatric population. So I created a knowledge graph for MGB data. I created another one for Boston Children. And the first exercise I did was to take ESR. And then I noticed that there's no overlapping loin code between the two institutions. They both use ESR. I don't believe that the ESR measuring for kids are actually different from ESR measuring for adults. I think it's because the two institutions picked two different loin codes. So in which case, basically, you can see even with both institutions, great infrastructure, you see huge amount of heterogeneity in how the concepts are presented. In which case, of course, if I were to run an algorithm, let's say I run COMAP or CASR at MGH, and I want to port that algorithm to Boston Children, I will realize they don't have that feature. And if we don't look at it, we wouldn't even know that we're missing that feature. So that's the, like when we did a sanity check and realized that there's so much heterogeneity, and some of which even common ontology, just because it depends on at what level of granularity we want to analyze as human or as researchers. So that motivated us to develop a framework to think about how we can borrow machine learning and the success of all these large language model or any of the AI models, and try to see, can we build some kind of framework to allow us to represent all these codes in a joint, in a harmonized version, so that when I look at a code of ESR at BCH, even though it's using a different loin code, it actually gets a very similar representation if I have a code of a different loin code at MGB. So that is basically what behind this, we call it graph alignment for multi-institutional data. And our goal is to enable us to perform collaborative learning across multiple institutions in the presence of heterogeneity in our coding system, including language. It also helps us to improve the interoperability. So in other words, the actual code that we select for ESR at the two institutions are different. But as long as their representation are very close to each other, it almost doesn't matter. So in which case, it automatically harmonizes the two representations. And we did many downstream studies in order to achieve this. But I want to just show you what are the input and what are the output. So we worked with many different hospital systems here. There are 7 of them, including summary level data. As Griffin had mentioned, it's actually the same summary level data that went into Kessler. We had Boston Children's, Bordeaux, through our collaboration during COVID. Duke, Mass General. We also use MIMIC data, UPMC, as well as VA. Through this exercise that you can see here, that there are many common ontologies like fee code. We roll up the ICD code to fee code. We roll up procedure to CCS, et cetera. But there are also many, many local codes that they may or may not mean the same thing. That's another exercise. I see colleagues here from UPMC. And when I was working with my collaborator, Zhongqi Xia, on the treatment for multiple sclerosis, we realized that we forgot, actually we didn't know their medication used J code for infusions. So that's like after we were almost done with the project, we realized we missed the J codes. So that's where they will go to the so-called local codes because we didn't know. And at the end of the day, you can see there are a total of about 50,000 concepts, some of which are overlapping. We have summary level data aggregated from a total of about 24 million patients. But the summary level data size is actually not so large. For example, at the VA, even though they have 12.5 million patients, but the aggregated summary level data is like 8,000 by 8,000 matrix. We did also include a textual information about the codes. Part of the reason I know that they are both ESR because there is text underneath every code that we have. So we did leverage language model to represent the EHR codes. We also use a lot of knowledge graph information. For example, from hierarchy, I know that all these loin codes all belong to ESR. So naturally, that will force me to represent the different loin codes that share the same LP parent code to be very similar. We use in unified medical language system, we would know, for example, rituximab has been used to treat these conditions. We know methotrexate is used to treat RA. So they have many relationships we already know throughout the UMS, and we borrow that information. At the end of the day, we also used actually a lot of information using ChatGPT. So a lot of the summary level data, for example, here, we would know, like for this condition, these are the features important for the disease, and these may not be so important. In that regard, EHR is amazing. EHR actually does much, much better than most other language models to say which ones are more important than others. So if you take a summary level data from EHR, you'll know if you sort them according to the output from the EHR, it does an amazing job compared to all the other language models like BERT, many variants of BERT, because that's really reflecting how physicians are treating their patient. But that information is noisy. Sometimes there's information that's basically unique to an institution, for example. So we actually run through ChatGPT to say, okay, these are the top 100. Can you tell me which ones are very important, which ones are not important? So we use that as another layer, silver standard label, to further enhance the training. So at the end of the day, we actually created a joint representation of EHR concepts across institutions. So the underpinning concept that we have is that, if you want to look at rheumatoid arthritis as a disease, we hope that our understanding of the disease is the same across healthcare systems, even that the code behavior might be different. So that is basically why we chose to use the same representation for shared ontologies. For example, fee code 714.1 is rheumatoid arthritis. We only have a single representation. However, if there is a J code for rituximab, we expect that it will be learned as closely as possible to the axonome code for rituximab. So this is basically the ultimate goal, that for local codes, if we happen to know what they really mean inside the common ontology, we hope that they have very close representation. So in which case, if we take the representation as a feature in the future, we hope that at the representation level, that they are much, much more transportable across systems. So here, I just want to show you like the upper left or right? Right corner is basically our knowledge graph representation. So we did a visualization. You can come to the website. You can search to say, I want to study this disease. What are the concepts? So each of the node here is a concept. And that's basically our final knowledge graph. We evaluated the performance of the embedding in many, many downstream tasks, including, for example, detecting similar or related concepts. So these are the circles comparing different methods. Our game is the outer green circle, and the darker orange one is OpenAI embedding. So we use that as a benchmark. And you can see that the left circle is to evaluate similarity. So language models are very good in understanding what are the synonyms. Similarity, so you can see that we can do similar comparable to OpenAI, slightly worse. But on the right-hand side is ability to understand relatedness. Is this drug related to that disease? So that you can see, we do much better than OpenAI embeddings, because that's where we borrowed the EHR information. So this is almost showcasing how much EHR summary level can help us. The next one I want to show you, we did, in this iteration, we took local lab codes at the VA, and we compared against the OMAP mapping that's curated within the VA. I do want to say that you have to take the OMAP mapping with a grain of salt. In fact, there are actually a lot of incorrect mapping. And here we are evaluating from the COMAP embedding, basically top K accuracy. If you were to come here, take a local code, a map to loin code that we have as gold standard, what's the top K accuracy? So you can see that game is actually doing very well. Again, fairly comparable to OpenAI embedding, because this is a similarity task. The next one is that feature importance. So Griffin mentioned that we actually want to understand how important are the features for a disease of interest. So this is basically doing a more of a feature selection jointly using data from multiple institutions. And here, I'm actually showing you the result instead of just asking OpenAI or asking ChatGPT how important it is. I'm showing you that I asked all the models to pick their top embeddings, and they have cosine similarity, so with some kind of rank orders. And then we compare against what we actually observe in the EHR. If you take the disease and you take the outcome of interest, here we're using the actual label, because we do have actual gold standard label for the 8 diseases. So we take the actual gold standard label against each of the features, and we're measuring the concordance of the label against the feature. So you can see game actually did a lot better, even compared to OpenAI. That's just at the embedding level. So the last thing I want to show, I think that's the most exciting thing for me, because so far it has been very painful to actually jointly do federated learning. So there are many, many things that we have overcome over the years. We know how to jointly train a neural network model, doing some few shot training, etc. But most of them relies us to have the same input. You have variable 1 to 10, I have to have the same variable 1 to 10. But as you can see from my earlier presentation, you sometimes don't. You have a different code. I don't even know that you have a different code. So this is to show you that what we did is that we were interested in clustering patients who were newly diagnosed with Alzheimer's disease. We take the baseline is first ICD code of Alzheimer's disease. We go backward for 2 years. We look at that 2 years worth of data and predict their future risk of nursing home admission. And in which case, each of the institution could have their own code. They could have local code. So our embedding already embedded every single code there is. There's some local codes, some shared ontology. We used this to do a simple TF-IDF multiplied by the cosine similarity between each of the feature and the AD code. So that's representing how important they are relative to the task I have in mind, which is clustering AD patients. So you can see that here, I have 3 institutions. We have UPMC, a cohort of AD patients, MGB, and we also have collaborators at Duke. So these are done federated manner. They have their own data. And what we did is basically we aggregated the counter level data, we multiplied that with the embedding, we create a patient embedding now. So each of the patients within each of the institution has their embedding. We did a federated t-SNE together with k-means. So all the we trained an autoencoder to do t-SNE so that we can do federated t-SNE. But in the end, basically our goal is to cluster patients into two groups, fast decline, slow decline. And here, I want to show you the results of the 3 institutions. So basically, these are the Kaplan-Meier curves from time 0 to nursing home admission. And also, the left-hand side is basically the hazard ratio of the clustering. So you can see that we basically can show that you actually identify fast decline and slow decline subgroups through federated learning without forcing them to have the same input feature. And the bottom line show you that you can actually go back to the original feature that went into your data. The left darker, the leftist 3 circles are the common ontology. So they have the same code. And you can see that the relative importance are fairly similar, although we never force them. On the right-hand side are the circles that now you have local code. They don't share with each other. We don't actually know what they necessarily mean, but you can see that it does pick up signals from their local codes as well. I just want to end. We did have another case study on suicide risk prediction. We found a similar performance. So I just want to conclude by saying that we started with COMAP, which can facilitate so-called online training and also can do validation with summary level data. But we are building on top of COMAP concept to say, can we actually now go one step further to make sure that when I miss some local important code, I don't have to worry so much. My algorithm hopefully can recover at least most of the signal. And we are in the process of collaborating with many more institutions because the ask from the local institution is relatively small. So what we learned, is particularly through our amazing collaboration with my VA colleagues, is that their data is so complex. And we are so much constrained of what we can do. In the end, the ask of each of the institutions have been super simple. So what we did, the only ask from each of the institutions is actually a co-occurrence matrix of codes. So we did manage to have co-occurrence constructed from Bordeaux in France. My postdoc did go there for a month, sit with them just so that they will actually keep working on it. And the result was very good. We also look at like a Bordeaux specific predictions. So we're definitely very interested in working with many other institutions. We have collaborators now hoping to join this effort from Italy and also Singapore, etc. And we'll be more than happy to chat if you are interested in contributing to this effort. Thank you.
Time for a couple of questions, and I don't know, Tianxi, if you want to use that microphone.
Yeah, sure.
Each have one.
I have a question. In practical, different hospitals has different structured data. So would you mind to share some experience or tips? How do you deal with the alignments to enhance robustness to make sure that we have a stable shared model in the end? Thanks.
So in the algorithms that are part of I2B2, you can run those internally within your institution, just standalone, and they will run okay. And then for most of the phenotypes, they work pretty well. That same algorithms can also work in a federated model. Essentially says there's a step in there where it constructs a co-occurrence matrix. So it's looking at all the different diagnosis codes, laboratory tests, procedures, and showing how many patients have those two things within a time window. It's only aggregate information, and if you combine those matrices between multiple institutions, then you can generate the feature list and the models in a more robust way than if you're doing them individually. There's several groups over here that are running the computed phenotype now and have constructed some of those co-occurrence tables. Once we get to a critical number, we'll put together a project where we do that and share those matrices and come up with like an I2B2 network-wide set of features, which would be, as a starting point for institutions or a more robust set of features that you might get if you're running this locally. And of course, you can then retrain those models and tune them with co-maps specific to your institution's data.
Thanks.
Thank you, wonderful talk. So when integrating multi-institutional EHR data, you talk about a game algorithm using graph alignment. So how do you compare the graph alignment with PCA or ICA-based method?
So because the information that we ingest is very diverse, there are like links. So they are binary, basically triplets, A, B, and there's a link. There's also like the PMI matrix, basically the co-occurrence matrix as embeddings, and then the language model, pre-trained language model also as embeddings. It's actually very complex. The diversity of the data actually makes it very challenging to use any naive idea. We actually, as one of the benchmark, we threshold everything into binary, like triplets. You can show it lost a lot of information. So you can also do PCA. It also lost a lot of information. I love PCA because it's so much simpler. Like I would much prefer to basically the least complexity of the model to achieve the reasonable performance. But this is one of the projects we do notice that there's a lot of gain through graphical neural network.
Thanks. In the T-SNE space, you talk about using k-means clustering for patient stratification. So how about using non-negative matrix factor algorithm?
That's a good question. I did not specifically compare to non-negative factorization. At that particular step, you don't have to do T-SNE. You can also do UMAP. You can also do other things. It's really our first proof of concept to say, if I do an efficient dimension reduction, what can you achieve? We did many exercises. We don't see a huge difference between T-SNE versus UMAP. We do see information loss by doing linear PCA.
Thank you.
So I'm wondering, can you do parametric modeling of the survival curves with this approach?
From where?
Well, you have all these features, right? You're coming up with survival curves. Can you do parametric modeling of those curves?
So just to clarify, if you want to start from the raw feature, you can definitely do that. So from like a clustering, from the very raw feature, right? We went through this exercise of ingesting the embedding, then we create patient embedding, right? From patient embedding, we want to predict the survival curve. So at that point, you can do whatever you want. Like clustering is just a simple way to show it. You can do parametric modeling, like also federated learning. There are many, many federated learning algorithms we can use. But the key here is to really say that, is there a shared model that can achieve a good accuracy without us to manually harmonize the feature? So if you want to go to very initial step, take all the original features, then I cannot create a joint model because the codes are even different. So I think it depends on which step you want to rewind to do the prediction. But if you take the embedding, yes, you definitely can. You can run Cox model, you can run many different models.
I just mentioned right before, and there's a workshop tomorrow morning, it's 9 o'clock, where I'll be going into a little bit more detail about the stored procedures and scripts you have to run within I2B2 to implement this computational phenotype pipeline. Today was much more on the methods and the algorithms, and tomorrow's more on details of how you would actually do this at your institution using I2B2. So thank you.
Thank you.